Welcome to In 5 Minutes. Let us continue with the discussion on parameter definitions. I will once again take the FM signal expression that we have just derived. We defined frequency modulation in the previous video clip. We will now define a similar parameter which is called phase deviation. So as you can notice this time, phase deviation, which will be writing as delta P, will simply be defined as the maximum deviation of the total angle of the modulated signal. This is a modulated signal. The maximum deviation of the total angle of this signal from the original carrier angle, which was simply equal to 2 pi fct. So for our reference, I will once again write down the carrier signal, which is Vc t equal to Vc cos 2 pi fct. So if you observe carefully, the original carrier signal had the total angle of only 2 pi fct, but now the modulated signal has this extra term in the form of phase angle. Whatever maximum value this extra phase part will take will become the phase deviation. So we define phase deviation delta P as nothing but the maximum value taken by mu f sine 2 pi fmt, because we still have the original angle of 2 pi fct present as it is. Now we can see that mu f is a constant, so it comes out, and maximum value that a sine function will take is equal to 1. So we get delta P equal to mu f. And as it turns out that the phase deviation is nothing but the modulation index, because the mu f we have already defined as modulation index. So we have got two important expression. Delta f, which was the frequency deviation, turns out to be mu f into fm, and we just now derived the expression of phase deviation, which is equal to simply mu f. So if you see the ratio of frequency deviation to the phase deviation, mu f will cancel out and the ratio turns out to be fm. But I repeat, this is only valid when modulating signal is of single frequency signal, the frequency being fm. Let us continue with the parameter definition. We will next define again a very important parameter, which is called frequency sensitivity. Let us define it first and see what notation we use to represent frequency sensitivity. It is defined as the ratio of frequency deviation. Frequency deviation was written as delta f. So it is a ratio of frequency deviation to the maximum amplitude of modulating signal. So let us quickly recall the modulating signal that we had taken originally. The modulating signal expression that we had taken originally was nothing but m of t equal to Vm cos 2 pi fmt. So what is the maximum magnitude of the modulating signal? It is nothing but m of t. So my definition of frequency sensitivity will be ratio of frequency deviation to the maximum amplitude of modulating signal, which is Vm. Now let us quickly figure out what does this ratio represent in terms of notations. If I want, I can use some new notation, let's say in the form of a constant k, but it is not required because we have already defined this ratio in the form of some important expression. So let us see what is delta f by Vm. Now if you remember, we have just now calculated delta f as mu f into fm. Going ahead, if you remember, we had replaced one expression of constants using mu f. That expression of constants which was replaced with mu f was nothing but kf Vm upon fm. So kf Vm upon fm was a term of constants which we had replaced with a single notation mu f. Hence, if I want to find delta f in the form of new expressions, then I can replace mu f again with the same term of constants and multiply this by fm, which is already there. So you can now see fm will cancel out, and the same delta f that we had written as mu f into fm will now become kf into Vm. And hence, if you see the ratio delta f by Vm points out to nothing but the constant kf that we have been talking about in the expression of fm. So the frequency sensitivity is nothing but kf. The constant that we have been using represents the frequency sensitivity. Now what does this parameter signify? It simply tells us that for a given value of Vm, how large is my frequency deviation in the fm signal. So for a constant value of Vm, if my delta f, if the frequency deviation is very large, then the frequency sensitivity is also very large. And as you can see, the frequency sensitivity will be measured as hertz per volts. It is delta F, which is measured in hertz, and maximum voltage, which is measured in volts. So it is very obvious that if you increase the maximum amplitude of modulating signal to achieve the same value of frequency sensitivity, you will have to increase the values of delta F also. But remember, modulation index has nothing to do with KF, because please remember that modulation index in that case will start increasing, because if you increase delta F, and even when you're changing the modulating signal amplitude, but if FM remains constant, with increase in delta F, mu F will increase. So if you increase Vm and delta F together in the same proportion, the Kf will remain constant, but mu F will increase as long as Fm remains constant.